that is your handy dandy reminder for these are always available later if you missed anything on YouTube or if you're sick or away. We're on TV. Okay, cool. So we just have a couple reminders today, get us started. So just remember your quiz is open, just like last weekend, like every weekend, just a couple questions. So since we actually had 3 days this week, it'll be 9 questions instead of 3 like last time. I think we kind of glossed over this when we read through the syllabus, but just so you know, you can use notes and stuff on these quizzes. So now that we're moving into the groove, good time to remind you guys about that. If you haven't been vaccinated and you want to be, you can go get vaccinated today. I just got a reminder email that that's open until 2. And third thing, I'm sure there are fun college things that I don't know anything about, but there's Fall Fest happening in Chester Bowl tomorrow. Last time I went, I got to bet on which square a chicken would poop in. That was very exciting for me. Also found some mushrooms in the woods. So if you're bored, it's over there. Any questions before we get started? Cool. All right, so when we broke off, we were, actually I'm going to draw an enzyme first. We were talking about enzymes. Right, so I just want to remember what an enzyme looks like, right? So we have our enzyme, which is a protein, right? It has an active site. So this active site, this is the active site that I've drawn there in the center. That's the spot, right? And what's this active site for? Someone remind me what binds in here? Starts with an S. Substrate. Yeah, our substrate. So write down active site, and then our substrate would go here. Cool. Right. So remembering the purpose of our enzymes, right? The enzymes are involved with changing the speed of chemical reactions, right? And the way they do that is by affecting our activation energy. So when we're thinking about the activation energy, I want to think about what happens when the activation energy is high versus when it's low, right? Because we know that the enzymes, what they're affecting is how high versus low that activation energy is. We're thinking about the reaction where we have a really high activation energy. It can be a fast one with a high rate of reaction, slow one with a low rate of reaction. Is the activation energy not going to affect the rate of reaction, or is this reaction unstoppable? Got a couple people in there. I'll move forward in a second. Don't have a good way to answer, just answer in your head. Okay, so activation energy, when it's high, what that means is you have to accumulate a lot of energy right? And that takes time, basically. So if we have a high activation energy, that means it's going to take longer for this reaction to happen, which means our rate of reaction is going to be low, right? Because it takes us time. It's kind of hard to get over that big hump, right? Just like biking over a hill, right? If you have a high hill, it's going to take you much longer to get to the other side of the hill than you have like a little bitty pretty flat hill, right? That's going to happen faster. Your rate of reaction, your rate of getting over the hill would be faster if that hill's lower. Does that make sense? So pulling that in with our enzymes, right? The enzyme changing the rate of reaction. So which of these things are in turn going to affect what the enzyme is doing, right? So our enzyme is our catalyst for the reaction. So we know it's lowering activation energy, but the enzyme itself, its rate can change. And this is like right where we ended on Wednesday, basically. We were kind of drawing a graph that was really. Okay, take another second, answer in your head. Okay. So when we're looking at the catalytic rate of the enzyme, right, the graph that we were drawing, I'm going to kind of draw it in the corner here, right? What we were looking at was our concentration, right? And in this case, we were looking at substrate concentration, right? And we were looking at the rate of reaction, just kind of related to the effectiveness of the enzyme, right? It was here. Right? So what we were looking at is the fact that our substrate concentration, as it goes up, right, our rate of reaction goes up. So our substrate concentration does affect our rate of reaction because it affects the catalytic rate of the enzyme. And then we drew a second line, right? So we drew a second line that was something like this, right? And what we were looking at was difference in affinity of the enzyme for the substrate, right? So we had our low affinity down here, right? They don't like each other that much. We had our high affinity up here. Okay. So the affinity does affect the catalytic rate of the enzyme as well. Here. Doesn't matter, right? So affinity check also affects it. So the one that we didn't go over but also has an effect here is that the enzyme concentration is also going to make a difference. As you have more enzyme, our reactions are going to proceed faster as well. Basically, because how fast the reaction happens is really just affected by how easy it is for our enzyme to find and bind onto a substrate. So anything that affects that is going to affect our catalytic rate. It's going to affect our rate of reaction. So there are lots of ways we can get those enzymes and substrates together faster, right? We can make them like each other more, make them magnet to each other, kind of, right? That's the affinity. We can have more substrate, right? And then they're just more likely by chance to find an enzyme. We can have more enzymes. They're more likely by chance to find a substrate. This is actually also why like temperature affects rates of reaction as well, because temperature just makes everything move around really fast. So they're more likely to bump into each other just because they're getting to more places, basically more quickly. Okay. So the one thing on here that doesn't affect it, yeah, is the activation energy of the enzyme. That's not really a thing. The enzyme is affecting activation energy, but it doesn't have an activation energy of its own. So as we move forward, right, if we kind of understand what the enzymes are doing, if they're lowering activation energy so that reactions can happen more quickly, we have different things that are kind of affecting their ability to speed up reactions, the concentration of their substrate and the enzyme, temperature, pH, right? Those are kind of these external factors. We also have ways that the body deliberately regulates enzyme activity. So even though temperature, for example, affects the rate of reaction, right, it's not useful for your body to like try to give yourself a fever whenever you want a reaction to proceed, right? That wouldn't be a great way of regulating things. So instead, these are the things we're going to do on purpose. We're going to regulate enzyme activity through something called allosteric regulation, which is basically what we'll go through picture, but you're going to kind of bind something on in a different place than we bind on the substrate to change the effectiveness of that enzyme and to change its affinity for the substrate. Covalent regulation is super similar to the allosteric regulation. I might even almost consider it a subtype. It's that we covalently bond something on. In allosteric regulation, it's not necessarily covalently bound on. And then we have feedback and feed forward inhibition and activation, respectively. These are kind of going to be like negative feedback loops for enzymes specifically. And the feedback inhibition in specific is really similar to our negative feedback loops that we're looking at conceptually. But basically, these are going to change concentrations of products we're going to see sometimes have effects on either earlier steps or later steps of our reaction. So those are going to be kind of two little loops that can affect our enzyme activity. So if we're looking at our enzyme here, we're starting with the allosteric regulation. Okay, so here's our enzyme with its active site. All right. What we didn't draw on before was a regulatory site. So this regulatory site is a point at which another molecule or an ion or something can bind on in order to affect the enzyme and its effectiveness. So you can see here after this modulator binds into the regulatory site, we've changed the shape of the active site. And the effectiveness of proteins in general and enzymes specifically is all about shape, right? It's all about how shapes fit with each other, what different shapes can do. So when we change the shape of this active site by binding something into this regulatory site, this is going to affect how well the enzyme can bind its substrate. So allosteric, sometimes it helps to break down word roots, right? Allo means like other, and steric refers to like a place. So it's really saying like other place regulation is what that word technically means. Actually, any questions about that allosteric regulation? Yeah.
Does it change the effectiveness
Of the enzyme, yeah. So like this change in the active site could change what can bind in there, or could change its affinity for that substrate, right? And that's why we were drawing those two affinity curves for the substrates, right? So if we changed, you know, that substrate line from the low affinity to the high affinity line, that would speed up our reaction. Or if we changed it from having high affinity to low affinity, then that would kind of slow down the rate of reaction. And if we change it a ton, right, like maybe we can't even bind the substrate or something. So it's not just about affinity, but that's the main way we can think about it. So with covalent regulation, this is very similar to the allosteric regulation, but basically this is going to be kind of more of a long-term change, is how I like to think of it. Because what we're doing, we still have our enzyme, it still has its active site, and we're actually still going to see a change in that active site, right? So here's our active site, right? And we can see on the other side where we see our enzyme, right? We're still talking about altering the activity of the enzyme, right? So we're altering its effectiveness, altering its catalytic rate, and therefore altering rates of reaction. The only real difference here between the covalent regulation and our allosteric regulation is that we're covalently binding in a group here, right? So here at this point, we're going to bind in that chemical group. Remove that there. So that's what we're saying with this kind of loop structure here, right? So we go from this situation where we have the chemical group and our enzyme not bound to each other, and then another enzyme helps us form a covalent bond between that chemical group here, and now it's actually stuck on, and so this enzyme is going to have that altered activity until another enzyme physically like grabs that modifying chemical group and pulls it off of our original enzyme. So this would have longer term effects, right? Because we have to use these other enzymes. This process like requires kind of more actors happening. So just tip for something people sometimes get confused about. So like when we're thinking enzyme, we're thinking covalent regulation versus allosteric regulation, rather than like when we're thinking about chemistry, covalent versus ionic. That's not really the difference there. Covalent versus allosteric are kind of paired ideas here in enzyme biology. We do have two kind of very common types of enzymes that we see involved in here. So I'm going to flip back to the previous slide for just a second. So what we're labeling here in red is these enzymes A and B that are either helping us add on a chemical group or remove the chemical group, right? So usually when we say a chemical group, what we're actually adding on or subtracting is a phosphate, right? So here we can see if we add on a phosphate, we're going to use a protein kinase to do that. So I believe on the previous slide, that's your enzyme A, the one on top. Like the protein kinase is a type of enzyme that would assist in forming a covalent bond between a phosphate and our original enzyme. And then when we want to remove that phosphate group, we're going to use something called a phosphatase. Phosphatase removes. So that's probably the easier word to remember, right? Because we have the phosphate in there. And ACE is always about breaking things down, basically. So we can see there's an ACE in the protein kinase, but Ray is talking about protein, right? Doing different stuff. That's referring to more about the enzyme. That term's not terribly helpful for remembering its action. But the phosphatase removes our phosphate. Does anyone want to see the previous slide again and match that up, or do we kind of get it? Oh, yeah, you do. Cool.
Well, I was just wondering, you said the chemical group is the phosphate.
Yeah. Yeah, so our phosphate here is that chemical group. Conceptually, it could be something else, but in biology, it's almost always that phosphate. So that leads us to our final two kind of bullet points on ways we're regulating enzyme activity. So the reason we're going to use feedback and feed-forward inhibition is that when we're talking about cells, when we're talking about physiology, we're usually not talking about just one single reaction, one single reactant that we're trying to turn into a product. And we're going to go into metabolism next. I'm sure you guys at least vaguely remember thinking about how we break down glucose and we have all these, tons of steps that it takes to eventually turn that into ATP, right? So when we're thinking about physiology, when we're thinking about how the body functions, we're really thinking about a smooth pathway, right, of reactions. So we're turning A into B, then we're turning B into C, C into D. So what your body is trying to regulate is that whole pathway, and that pathway can move without kind of stops and starts. We want to move that smoothly, and we'll want to regulate this whole pathway according to what the body needs. Sometimes we won't need to be doing metabolism so quickly, right? Like if I'm laying around in my bed, I don't need that much energy. If I'm out on a run, I need more energy. So it depends what you're doing. So your body's going to change these reactions based on what it needs. But in order to proceed these things smoothly, we're often going to have some of these like intermediate products that loop back and have an effect on a previous reaction. So here, what this is saying, right, is we're turning A into B using enzyme 1. We're turning B into C using enzyme 2, and C into D using enzyme 3. So that's what those E's are. E is for enzyme here, and we just have enzymes 1, 2, 3. So in this little example, we're saying that enzyme 1 and enzyme 3 are just kind of chugging along at constant rates. We're not worrying about how they vary here. But we see that little looping arrow in the center, right? So what that is telling us is the rate of enzyme 2 is actually affected by how much enzyme C there is, right? So how effective this second step is, right? How effective that second enzyme is going to depend on how much C there is, right? Because you can see this minus sign here, right? What did we learn about minus signs before? Like what kind of a loop was that, right? What kind of feedback was that? Yeah, so we can tell that this is kind of a negative feedback loop here. And so when we're talking about enzymes specifically and reactions, this specific type of negative feedback is our feedback inhibition. So what we're saying here is as we have more of enzyme C, what's going to happen? Sorry, more of this product C, this intermediate product. What's going to happen to this reaction? Is it going to speed up or slow down as we have more C accumulating?
Slow down.
Exactly. Yeah. So that's all that we're talking about here when we're talking about feedback inhibition, basically, is when we're producing something that then kind of loops back and slows down a step. Basically, it would do this through, for example, that allosteric regulation, right? Like maybe C binds into a regulatory site somewhere on that enzyme too. So that's how it would do that. So the last thing here is we would call this the rate limiting step, this B to C, because this is the one that we're varying. This is probably going to be slowest, right? Because as we're building up C, it's slowing down that enzyme too. And we need C in order to proceed to D, which is our final product. So how fast this enzyme can do its job, right? How fast this B to C step proceeds is going to affect how fast the overall reaction proceeds. So here we have a different example of feedback inhibition. It doesn't always need to happen in the middle there. It can happen between kind of any set of steps. So here in this form of feedback inhibition, which product, which chemical is doing the inhibiting here? Yeah, exactly, D. So when we get the final product, that's looping back all the way to the beginning and affecting that first enzyme, right? So it's going to be affecting that enzyme 1. So basically what we're saying is we're going through this whole pathway, A, B, C, D. We're trying to ultimately make B from A. But once we've done it, we kind of want to stop. It's like, you know, we did it already. We don't need to keep doing this. So we have this negative feedback loop, specifically called feedback inhibition in this case, that turns it off at the beginning.
So how would we affect
So in this case, we have minus sign, so it says it's slowing it down, basically. So that's why this is great for
But does it modify the enzyme or?
Yeah.
Okay.
Yeah, just like the previous one, it could be doing probably allosteric regulation, but maybe there's another enzyme helping it do covalent regulation. But yeah, basically it's just affecting it by changing the shape of the enzyme. Just like positive feedback was rare, feed forward activation is also rare, but it can happen. So we're seeing minus signs before, and we're seeing a plus sign. But conceptually, we're still talking about regulating how well an enzyme works. So in this case, as we're building up more B, right, as concentrations of this B start to rise, B shoots forward a little bit and tells enzyme 3, hurry up, we're going to need you, start working better, right? So it's feeding forward, letting those future steps kind of speed it up. So we don't always make enzymes less effective. We can also make them more effective, and we can also affect future steps, because we don't usually do it that way, but it doesn't mean you'll never see a pathway that works like that. The question about enzymes broadly, any of these reaction kind of terms before we move into our specific example of metabolism.
Forward on the feedback. Does it only slow down? Like, now I'm seeing another one, I can speed it up. With the feedback, does that only slow down the previous step? It can't tell it to like hurry up a little bit if it needs to.
So inhibition always means slowing it down. So yeah, so feedback inhibition is kind of telling you that it's going backward, and the inhibition part tells you it's slowing it down. I don't know of any examples where we go back and speed it up. That doesn't mean they don't exist. I do not have all the pathways in every cell memorized, but this is how you do it.
So it's two separate things if you need it to speed up, that's different.
Speeding it up is activation. So when we say something activates something, right, it makes it more active. It gives it more energy. So speed it up. If you inhibit something, right, like if you have a lot of inhibitions, you know, you're at a party, you have lots of inhibitions, you kind of sit in the corner, right, you don't want to talk to anyone, right, so that's slowing it down, like lowering rate.
E1, E2, and E3 are enzymes, but what are E2 and E?
These are just like different molecules. Like as we start to talk about metabolism, right? Like maybe we have our glucose, our pyruvate, and so on like that. So that's our kind of main pathway of chemicals we're going to be talking about. And more enzyme stuff. In that case, we'll move into metabolism. So really what we're going to be talking about is cellular respiration. At the very end, we'll talk about how we can break down a couple of other things. But we're really going to be doing glucose metabolism for almost all of this. So I'm going to take a second. I know you've all seen at least a little bit of cellular respiration before. So go ahead and jog your memories and just check for yourself how much of this stuff you remember. And if you have any things that you know you don't remember, write them down for yourself now and make sure that you get it as we go over it. I know it can be hard to remember what you don't remember. So why we're focusing on what we can remember first. Okay, start taking a look. Okay. So objectives, right? Basically, the big main thing we're going to care about as we go through this is ATP. So we're doing this whole thing because we care about how cells get energy that they can use in all the different organ systems, all the various physiological processes that we're going to talk about in the future. And to do pretty much anything at all, they're going to need energy, they're going to need ATP. So that's why we start with a metabolism step. So we're going to go through the different events in glucose metabolism. So the breakdown of glucose metabolism, talking about how we break it down. So for the purposes of this class, the steps are glycolysis, our linking step with pyruvate, the Krebs cycle, and oxidative phosphorylation. I know different books, different classes use different terms for some of these. So like the Krebs cycle, it's also the citric acid cycle, so the TPA cycle, oxidative phosphorylation also includes chemioosmosis. So those terms are, if you wrote them down, they're not wrong. But we'll go through the terms specifically that we'll be using here. And at the end, we'll talk a little bit about fats, proteins, and glycogen and other ways the body is able to store and release energy. So we're going to start with glucose and ATP. Glucose is great. Carbs are great, right? Glucose is carbohydrate. So our central reaction in order to produce ATP, so the key part of energy metabolism of making energy, making ATP, is we have glucose, C6H12O6. We're going to use oxygen. Cells are usually going to do aerobic respiration, although we'll talk about cases in which they don't. We're going to produce energy plus some byproducts, specifically carbon dioxide and water. So if we look at this reaction here on the bottom, right, what we're doing is oxidizing glucose technically. So you might also call this reaction glucose oxidation. You might call it aerobic respiration. You might just generally talk about cellular respiration. Those are all kind of getting at the same key concept. Very similar terms referring to the same process. But what we're saying is we're taking these reactants, we're turning them into these products, but the one we care most about is our energy. Some of it we lose by heat, but really we're shuffling this energy by shuffling around electrons, and we're using it to take a molecule that we already have kind of floating around in the body, ADP, adenosine diphosphate. So we looked at that as one of our examples of like a modified nucleotide when we're looking at nucleic acids. We're going to tack on another phosphate group to make ATP. This, so we care about all the time in the body, because this is our form of cellular energy. When we use that ATP, we break off that phosphate group. So the ATP turns back into ADP. And breaking that bond, that last bond between our phosphate groups, because what we really have is like adenosine, right, bound to a phosphate, bound to a phosphate, bound to a phosphate. This is the ATP. So what we're talking about is forming or breaking this bond. When we have two, that's our ADP. And when we have three, that's our ATP. And we will have to remember this again in the future when we talk about muscles and how muscle contractions happen. These two different forms, ADP having less energy, ATP having more energy, are going to come back and play kind of a somewhat complicated role in the future. But so we'll talk about them more when we get to them there. Here we care about the fact just that we're tacking on an additional phosphate group to make ATP this form of cellular energy. Okay. So ATP is the way in which we're exchanging energy in the cell. So what we're doing is we're basically like trapping energy into this form of ATP. So when we say we're using energy from exergonic reactions, it's helpful to remember some chemistry words. So let's write some of those down, right? So we're going to want to remember what endergonic means. I remember what exergonic means. Let's also remember catabolism and anabolism. Does anyone want to take a shot at any of these words back from chemistry? Yeah, like when we're talking about ions. So when we're talking about it in the form of metabolism, is going to talk about breaking stuff down. So let's put that on there. Okay. But that's good for cations. Those are going to come back later. Yeah. But now catabolism, breaking down molecules. I can't spell molecules all of a sudden. That's not right, is it? Okay. So anabolism is going to be the opposite.
So that's what we're doing with anions.
Yeah, I mean, they're very similar terms. It's not super helpful to think about them when we're thinking about metabolism, unfortunately. But they do come from like the same root Greek words. And they probably are related in chemistry, but I'm not exactly sure how. I'm more of a anatomist than a chemist. I like big stuff I can see. Also, if anybody wants to do like research on bones in the future, come see me. Okay, so anabolism is going to be building bigger molecules. The only way I remember this in my head, by the way, is I think of my friend Anna, who's super tall, and I pretend she has a cat who's really short. And so I think about anabolism as being big and catabolism as being like a tiny cat. I don't know if that helps. Would help if we knew Greek. I do not know Greek. Okay. So endergonic and exergonic. Maybe we can guess from this sentence up here, right? If we say energy from exergonic reactions, another way we could get to what this word means, right? So let's look at this X. We've seen the word like extracellular before, right? So what does that X kind of imply to us?
Doesn't it mean that there's energy leaving the reaction?
Yeah, that X is always telling us like outside, basically. So an exergonic reaction releases energy. And an endergonic reaction requires energy. It like soaks up energy. Absorbs energy. Something like that. So those are just terms that you'll see sometimes as we're talking about these different steps, these different chemical reactions. So they're helpful to remember. I don't think there's a slide detailing those all out, but I could have forgotten what we wrote. It's possible. So does everybody have this down? So when we're talking about ATP synthesis, we're taking the ADP, adding in a phosphate group, we're adding in energy, right? So we're adding in energy, which means this is going to be endergonic, right? We have to put the energy into this reaction, and that gives us ATP. Later, when we use ATP, we're doing the opposite. So it's making the ATP with endergonic. What is using the ATP going to be? When we break that bond. Yeah, exactly. We're going to release the energy on the other side. And that's the whole point of the ATP, right? Is releasing the energy to do so. So ATP synthesis is a condensation reaction, meaning that we're getting water out at the end there, right? Condensation, like when you have it form on the outside of your water bottle, right? You're seeing water droplets form. Same thing here, we're having water form. We might also refer to it as a phosphorylation reaction because phosphorylation refers to the fact that we're adding on that phosphate group, right? So phosphorylation, there we go, our phosphorus. And we can do this two different ways, and we will see both of these in our glucose metabolism, in our glucose oxidation, in our, what other word do we use, our aerobic cellular respiration. Okay. So basically, substrate level phosphorylation, we're going to have an enzyme that we're using to do this, and we're going to kind of transfer a phosphate group from something else onto the ATP. So that's what the X is for. X is telling us that another molecule is holding that phosphate before. And that's going to happen earlier in our earlier steps of glucose metabolism. The other thing we can do at the end of aerobic cellular respiration So specifically, it's a step requiring oxygen. So you can do oxidative phosphorylation. In oxidative phosphorylation, we're going to be taking kind of 3 phosphate ions. And this is going to require the electron transport chain. And we'll talk about how it's doing that. But it's a different kind of way of getting phosphate ions and putting them onto our ADP. So substrate level versus oxidative phosphorylation. And this word substrate, right, like we just saw with our enzymes, so that can kind of help us remember that this is going to have to do with binding molecules on and then breaking those bonds, right, because that's what enzymes do partially. So when we break down ATP, we're releasing our energy, right? So we just said that's going to be exergonic. Because our creation of ATP was a condensation reaction, when we break down ATP, we're going to require water. So it's going to be a hydrolysis reaction. So hydrolysis means breaking down water, right? So lysis is always breaking something up. Hydro or water. Okay. So don't really need to memorize this equation, although it may help you remember some of the steps as you make sure that you're counting up to approximately the right level of ATP. But we're going to be looking next about energy changes in our glucose oxidation, in this glucose metabolism as we break down glucose. Right, so before, when we had this equation, we kind of just said, ooh, there's energy at the end. Now we know it's specifically 38-ish ATP. This varies on what tissue you're talking about, how old you are, what species you're talking about. So different places you look will have different numbers. That's because it can vary a little bit depending on how different membranes in different places work. So don't get hung up on that exact number. And now we've just written in that actually we're going to need to remember to put in our ADP and our phosphate ions in order to have something to make that ATP out of. So we could multiply this stuff out and figure out exactly how many calories are required for each of these steps. So the energy in 38 ATP, 38 moles times 7 kilocalories per mole is how much energy you get for each individual ATP would give you about 266 kilocalories. The energy released during glucose oxidation is more than that. So where do you think the extra energy that isn't getting turned into ATP is going? Why are those two numbers like not the same? So part of it is that we're losing stuff to body heat. And again, don't memorize these numbers. Basically, it's just not totally efficient because a bunch of this gets released as body heat, which conceptually we can kind of think of, right? Because we know if we exercise hard, we feel hotter, right? We feel that body heat building up. That's body heat partially being released by metabolism, also partially from friction from whatever you're doing, but some of it is that body heat from this production of ATP. We're going to get started on the steps. Let's try to take a piece of, I call it, yeah, go ahead. That we're losing some to heat. So you can see these heat steps going off. This isn't a totally efficient process. Yeah. Okay. So we're going to go through a number of steps as we talk about how glucose gets oxidized, how we break down glucose. We're going to talk about glycolysis. We have a sort of linking step involving pyruvate between glycolysis and our next big And then we're going to move into the electron transport chain. So these are the places we're going to see that we're going to be creating energy. We're going to be creating ATP. When we look at glycolysis in the Krebs cycle, you should know that those are substrate level phosphorylation. So that's referring to the method by which we create the ATP. So this is the part where we have those phosphate groups bound onto something else, maybe using like enzymes and stuff. And this is different than our electron transport chain, which is doing oxidative phosphorylation. So it has these free phosphate ions. And if you remember last time we talked about metabolism, we probably talked about your hydrogen ions flowing across a membrane. It was really about movement, right? We had a different sort of thing going on when we're making ATP in that final step. So we will start here next time, but just for right now, glycolysis, we're breaking down glucose, making some pyruvate, we're making some ATP. So immediately in the first step of glucose metabolism, we are making ourselves a little bit of ATP. Energy production starts at the beginning.